The universe is a vast, mysterious place, encompassing everything we've ever known, observed, or could ever hope to come into contact with. For millennia, a look up at the sky, our window into the cosmos beyond our world, was met with wonder, awe, and a fascination with the unknown. Thanks to all the scientific advances made by civilizations across the globe, we now know that the points of light in the sky are stars, found grouped together in galaxies, which cluster together on the largest scales in a universe that began with our Big Bang a finite amount of time ago, 13.8 billion years. However, knowing that doesn't mean we know everything. In fact, the more we learn about the universe, the more we realize it is not what we expected. Throughout history, our understanding proved to be wrong, and surprises never seem to end. Accordingly, the experts are confronted over and over again with entities and processes that take known conclusions to absurdity. This includes an equally interesting and puzzling spectacle that scientists recently uncovered in an alien galaxy. What makes this new discovery so confusing, and what does questions it raise? All this and more will be discussed in today's episode of Eyes 200M. For as long as humans have roamed the Earth, we have sought to find our place in the cosmos. From the city-states of ancient Greece to the soaring capstones of the Egyptian pyramids, across the deserts and towering mountains of ancient China, down to the rolling plains of Mesoamerica, humans have sought to understand how the universe works. They developed mathematics to trace the motions of the planets, estimated the circumference of the Earth by walking from city to city, created star tables and timekeeping codices, and even recorded celestial events like Halley's Comet, supernovae, and eclipses. With time, we have refined our models of the universe. Using ellipses, Johannes Kepler reconfigured celestial motions. Galileo revolutionized Copernicus's heliocentric model of the solar system by discovering that the Sun, not the Earth, is the body around which all other elements of the solar system orbit. Isaac Newton developed the theory of gravity, which was later supplanted by Albert Einstein's theory of general relativity. Discovery by discovery, we paint in the gaps of the picture of our universe. And yet somehow, with each brushstroke, that image morphs, evolving into something ever-changing, new, and unrecognizable. The universe that Kepler and Galileo, Copernicus and Kepler, Newton and Galileo, and even Einstein understood, is different from the one we know today. Today's understanding of the universe is unsettling. It is not one that fits in a tidy little box with neat lines and a perfect lid. Our universe is mystifying, complex. It defies expectations. For starters, our universe is not a static, enclosed entity. Our universe is expanding. From everywhere all at once, the fabric of space-time is stretching away from everywhere else, like an inflating balloon, carrying galaxies along with it. Photons traveling the lanes of the cosmos are stretched along with space-time, their wavelengths growing ever longer or redder, thus red shifting with the expansion of space. Our universe isn't expanding into anything. To our knowledge, there is no extra dimension around the universe. Rather, space itself is expanding, causing the space between galaxy clusters, the largest gravitationally bound objects in the universe, to get bigger and bigger with time. And this leads us to the following unsettling conclusion. There's no center to our universe. Everywhere is the center, because everything everywhere is moving away from everything else, all at once. But the universe isn't just expanding, it's accelerating. With each passing moment, an unknown, repulsive, persistent force dubbed dark energy is stretching the fabric of the universe. Dark energy is a fundamental property of space itself, invisible, smooth, and constant, and yet we are entirely unsure what it truly is. And then there is dark matter, the invisible, clumpy matter that binds galaxies together. In many ways, dark matter is the corollary to dark energy. where dark energy stretches space apart, dark matter knits matter together. They are both invisible, neither interacts with radiation or light, and yet they are ever present, dark matter acting as the cosmic glue for large-scale structure formation, and dark energy a principal ingredient in the universe's evolution. The afterglow of the Big Bang, known as the cosmic microwave background, is imprinted on the fabric of space-time, a relic of radiation from when the universe was extraordinarily hot, dense, and smooth. By mapping its bumps and irregularities and comparing with galaxy surveys, scientists have found that 70% of the universe is made up of dark energy. Meanwhile, 25% of the universe is dark matter. Just 5% of the universe is ordinary matter. The remaining 95% of the universe is stuff that we can't see, don't yet understand. As such, despite everything we've learned about our universe, there are many existential questions that remain unanswered. We don't know if our universe is finite or infinite in extent. We only know that its physical size must be greater than the portion we can observe. We don't know whether our universe encompasses all that exists, or whether it's only one of many universes making up a multiverse. And we remain ignorant about what happened in the earliest stages of all, in the first tiny fraction of a second of the hot Big Bang, as we lack the necessary evidence to draw a robust conclusion. But one thing we are certain about is that the universe has an edge, not in space, but in time, because the hot Big Bang occurred at a known finite time in the past, 13.8 billion years ago, with an uncertainty of less than 1%. There's an edge to how far away we can see. Even at the speed of light, the ultimate cosmic speed limit, there's a fundamental limit to how far back we can see. The farther away we look, the farther back in time we're able to see. And now, thanks to our best measurements of the part we can see, we're finally figuring out what lies beyond, and how much of it we'll someday be able to perceive and explore. But before delving into the unimagined object in space, you first note that when astronomers talk about the universe, they almost always mean the observable universe. The word observable does not refer to the capability of technology to receive signals from distant galaxies, or even if there is anything out there to be detected. Rather, it, as told, is a limit based on the speed of light itself. No signal can travel faster than the speed of light, meaning that there is a maximum distance since the start of the universe, beyond which nothing could have been detected. There simply hasn't been enough time for light to reach us. This distance is called the particle horizon, which is analogous to the event horizon of a black hole. The universe can be assumed to be isotropic in all directions, which means that every location has its own observable universe when considered as the center, or observer. When the world's most powerful space observation, the James Webb Space Telescope, focused its sharp infrared eyes on deep space, it detected a galaxy called JD's GSZ 13-0, found in the constellation Fornax. JD's GSZ 13-0 is amongst the furthest known galaxies from Earth ever discovered, and is at the edge of the observable universe. Due to the isotropic nature of space, if you were an inhabitant of this fairly small galaxy, the Earth would be at the edge of your observable universe. The light from JD's GSZ 13-0 was observed to be about 13.4 billion years old, less than 400 million years after the Big Bang, when the universe was only 2% of its current age. In fact, the observation of this galaxy so soon after the first stars were born presented a challenge to certain theoretical models of galaxy formation. One might expect that this age would mean that JD's GSAZ 13-0 would be 13.4 billion light-years away from Earth. However, the actual distance to the galaxy is 33.6 billion light-years. How can this be? If the age of the universe is roughly 13.8 billion years, surely there hasn't been enough time for light to cover such a distance. Difference between the so-called light travel distance and the actual distance is due to the expansion of space-time. Imagine two dots on a deflated balloon, each representing a galaxy. If we inflate the balloon, we would observe the dots moving apart. The rubber of the balloon represents space, meaning the very medium in which the galaxies exist expands. Edwin Hubble observed galaxies moving apart. And indeed, galaxies further away from Earth appear to moving away from us faster than galaxies which are closer. Hubble used the analogy of raisins in a loaf of bread, which is more accurate than the balloon example, as space expands in 3 dimensions rather than 2. Another important effect of the expansion of space is the effect on the wavelength of light. If we imagine a dash slowly traveling across the balloon between the 2 dots, it will get longer as the balloon expands. This is the same thing that happens to light as it travels. Its wavelength increases. The increase in wavelength and a corresponding decrease in light's energy is known as redshifting. It is by measuring the redshift of light from distant galaxies that we can derive cosmological distances. All this means that in the time it took for light to travel from JDES GSZ 13.0 to Earth, the distance between the 2 points in space has greatly increased. In fact, the distance from Earth to the edge of the observable universe is roughly 46 billion light-years. The observable universe will continue to expand as time progresses, but interestingly, we will be able to see fewer and fewer objects. The universe is expanding faster than the speed of light, and so galaxies at the very edge, which we can see now, will, in time, become more and more redshifted until they disappear, and we will no longer be able to receive signals from them. It has been calculated that the maximum distance from Earth, which will provide a signal that will reach us given infinite time into the future and accounting for expansion, is 16 billion light-years. This distance is known as the reachable universe. In other words, we could still reach galaxies closer than 16 billion light-years if we left Earth today. The future visibility limit, the distance beyond which objects will never enter the observable universe at any point in the future, is 62 billion light-years. This is exactly equal to the current visibility limit plus the reachable limit. And this is no coincidence. The light that will ultimately reach us is right at that reachable limit today, after journeying 46 billion light-years since the Big Bang. Someday far in the future, it will arrive at our eyes. With each moment that passes, we come ever closer to our ultimate cosmic viewpoint, as the light from the last galactic holdouts continues on its inevitable journey towards us in the expanding universe. A question to finish with. What is the true distance that light has traveled from JD's GSZ 13.0? If the speed of light is fixed and the time in which it has traveled is also fixed, how far has it gone while the space is expanding? But this is not the only puzzle that JD's GSZ 13.0 poses for scientists. A paper in April 2023 suggests that the most distant galaxy even seen taken by James Webb isn't in fact a galaxy, but a dark star with a mass of around 1 million times that of the Sun. Unlike ordinary stars, dark stars might not have been fueled not by nuclear fusion, but by the self-annihilation of dark matter, the invisible stuff that is thought to make up about 85% of the matter in the universe. The candidate star seen by James Webb will need more evidence to be confirmed, but if they're real, the finding could change our story of how the first stars formed. While waiting for scientists to solve these riddles, let's take a quick look at these new stunning images captured by James Webb. These unpredicted images caused a stir in the scientific community, as unveiling that newborn galaxies look weirder than expected. For the longest time, many astrophysicists and cosmologists have assumed that newborn galaxies would look like the orbs and spidery disks familiar in the modern universe. But according to an analysis of new images from the James Webb Space Telescope, baby galaxies were neither eggs nor disks. They were bananas. or pickles, or cigars, or surfboards. Choose your own metaphor. That is the tentative conclusion of a team of astronomers who examined images of some 4,000 newborn galaxies observed by Webb at the dawn of time. This is both a surprising and unexpected result, though there were already hints of it with Hubble, said Viraj Pandya, a postdoctoral fellow at Columbia University, referring to the Hubble Space Telescope. He is the lead author of a paper soon to be published in the Astrophysical Journal under the provocative title Galaxies Going Bananas. Dr. Pandya is scheduled to give a talk about his work on Wednesday at a meeting of the American Astronomical Society in New Orleans. If the result holds, astronomers say that it could profoundly alter their understanding of how galaxies emerge and grow. It could also offer insight into the mysterious nature of dark matter, an unknown and invisible form of matter that astronomers say makes up a major part of the universe and outweighs atomic matter 5-1. Dark matter engulfs galaxies and provides the gravitational nurseries in which new galaxies arise. According to Joel Primack, an astronomer at the University of California, Santa Cruz, and an author of the new paper, the result builds on hints from earlier observations from the Hubble telescope that the earliest galaxies were shaped like pickles. In an email, Alan Dressler of the Carnegie Observatories, who was not part of Dr. Pandya's work, characterized the result as important. It is important, extremely important, if it is true. The study team analyzed the images of galaxies in a patch of sky smaller than a full moon known as the Extended Groth Strip, which has been surveyed by many other telescopes, including the Hubble telescope. The images were obtained by an international collaboration called the Cosmic Evolution Early Release Science, or CEERS survey. The team plans to extend its observations to other well-studied areas of the cosmos. This will let us identify galaxies with different 3D shapes all over the sky and facilitate much-needed spectroscopic follow-up observations, Dr. Pandya wrote in an email. Galaxies are the city-states of the cosmos. Within the visible universe are an estimated 2 trillion of them, each containing as many as 1 trillion stars. But the visible universe is only a fraction of what's out there. Most of the matter in the cosmos seems to be in the form of dark matter. Whatever dark matter is, it constitutes the invisible bones of the universe we see. Astronomers now think that galaxies were seeded by random fluctuations in the density of matter and energy during the Big Bang. As space expanded, the denser areas lagged and dark matter pooled, pulling normal matter with it. This material eventually fell back together and lit up as stars and galaxies, or disappeared into black holes. The Webb telescope was designed to investigate this formative and mysterious area. With a giant mirror and infrared sensors, it can see the most distant and thus earliest galaxies. Dr. Pandya and his collaborators investigated the three-dimensional shapes of galaxies by statistically analyzing their two-dimensional projections on the sky. If these early galaxies were balls or disks randomly oriented in space, they should occasionally present their full faces, appearing round and circular, to telescopes. But astronomers aren't seeing much of that. Instead, they see lots of cigars and bananas. According to Dr. Pandya, they consistently look very linear, with some galaxies showing multiple bright clumps arranged like pearls on a necklace. Such oblong galaxies are rare today, but they make up as much as 80% of the galaxies in the CEERS sample, which reaches back to about 500 million years after the Big Bang. Their masses are such that they would be the progenitors of galaxies like the Milky Way, implying that our own galaxy may have gone through a similar surfboard morphological phase in the past. In the modern universe, galaxies seem to come in two basic forms: featureless, roundish clouds called ellipticals, and flat, spidery disks like our Milky Way home. Evidently, the earliest newborns didn't start out like that. The reason, astronomers suspect, is related to the properties of dark matter, but exactly which or how is unclear. The leading theory holds that dark matter consists of clouds of exotic subatomic particles left over from the Big Bang. Ordinary matter, drawn by gravity into these clouds, would condense and light up into stars and galaxies, according to computer simulations. In a popular variant called cold dark matter, these leftover particles would be heavy and slow compared with protons, neutrons, and the other, more familiar denizens of the quantum atomic world. According to computer simulations, cold dark matter would clump easily to form the large-scale patterns astronomers see in the sky. Identifying these slow, heavy particles would shake the world of particle physics and cosmology. But thus far, experiments in labs, like the Large Hadron Collider at CERN, have failed to detect or produce any particles of cold, dark matter. Lately, interest has shifted to other proposed forms of dark matter, including a whole gallery, a dark sector, of dark particles interacting with one another invisibly through dark forces. In this mix are axions, which in theory are extremely light and act more like waves than particles, fuzzy dark matter, or wavy dark matter, in the vernacular. In computer simulations of galaxy formation, such waves can interfere with one another, producing knobby filamentary structures instead of the round shapes predicted by cold dark matter. Yes, the dark matter connection is tantalizing, Dr. Pandya said, adding that the devil was in the messy details of gastrophysics, which describes how turbulence, hot gas, and magnetic fields interact to light up stars and galaxies. The mini halos of dark matter scattered throughout the cosmos could function as highly sensitive probes of primordial magnetic fields. This is also what emerges from a theoretical study conducted by CISA and published in the journal Physical Review Letters. Present on immense scales, magnetic fields are found everywhere in the universe. However, their origins are still subjects of debate among scholars. An intriguing possibility is that magnetic fields originated near the birth of the universe itself. That is, they are primordial magnetic fields. In the study, researchers showed that if magnetic fields are indeed primordial, then it could cause an increase in dark matter density perturbations on small scales. The ultimate effect of this process would be the formation of mini halos of dark matter, which, if detected, would hint towards a primordial nature of magnetic fields. Thus, in an apparent paradox, the invisible part of our universe could be useful in resolving the nature of a component of the visibly one. As Pranjal Ralagankar of CISA, the author of the research, explains, magnetic fields are ubiquitous in the cosmos. A possible theory regarding their formation suggests that those observed so far could be produced in the early stages of our universe. However, this proposition lacks explanation in the standard model of physics. To shed light on this aspect and find a way to detect primordial magnetic fields, with this work, we propose a method that we could define as indirect. Our approach is based on a question: what is the influence of magnetic fields on dark matter? It is known that there is no direct interaction. Still, as Ralagankar explains, there is an indirect one that occurs through gravity. Primordial magnetic fields can enhance density perturbations of electrons and protons in the primordial universe. When these become too large, they influence the magnetic fields themselves. The consequence is the suppression of fluctuations on a small scale. Ralagankar explains, in the study, we show something unexpected. The growth in baryon density gravitationally induces the growth of dark matter perturbations without the possibility of subsequent cancellation. This would result in their collapse on small scales, producing mini halos of dark matter. The consequence, continues the author, is that although fluctuations in the density of baryonic matter are cancelled, they would leave traces through the mini halos, all solely through gravitational interactions. These theoretical findings, concludes Pranjal Ralagankar, also suggest that the abundance of mini-halos is determined not by the present presence of primordial magnetic fields, but rather by their strength in the primordial universe. Thus, a detection of dark matter mini-halos would reinforce the hypothesis that magnetic fields formed very early, even within 1 second after the Big Bang. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.